In a water pipe, the length and cross-sectional area of the pipe determine the resistance that the pipe offers to the flow of water. For instance, if we shorten a water pipe, keeping its diameter the same, it offers less resistance to flow. And if we decrease the pipe's cross-sectional area, keeping the length the same, the resistance to flow increases. Think of sucking soda through a thin straw versus a thick one. The thick straw allows more soda to flow through with less effort. Analogous effects are found in the electrical case, where the size and shape of the resistor matters, but the type of material of which the resistor is composed also matters. For a wide range of materials, the resistance of a piece of material of length L and cross-sectional area A is given by R equals rho L divided by A, where R is the resistance, rho is the resistivity, and L and A are the length and cross-sectional area of the resistor as shown in the diagram. As we had learned earlier, the unit of resistance is the ohm, whereas the unit of resistivity is the ohm meter. The resistance and resistivity are related through the equation R equals rho L divided by A, but they should not be confused. The resistance R is a value assigned to an object that is a measure of how strongly it impedes the flow of current. It depends on the shape of the object and on the material of which it is made. The resistivity, rho, is an inherent property of a material. For example, rubber has a large resistivity compared to a metal such as copper. The metal and alloy conductors in this table, for instance, all have resistivities on the order of 10 to the negative 8 ohm meters, whereas the insulators, like rubber, have resistivities many orders higher at about 10 to the 15 ohm meters. Semiconductors range somewhere in between. Knowing the dimensions of an object and the type of material of which it is made allows us to calculate the electrical resistance of the object. For example, what is the resistance of a 1.0 centimeter length of circular cross-section wire made of nichrome alloy if the cross-sectional area of the wire is 3.0 times 10 to the negative 7 meters squared? We're given that the resistivity of nichrome alloy is 100 times 10 to the negative 8 ohm meters. We start with the relation that relates the resistivity to the resistance, or R equals rho times L divided by A. This is equal to 100 times 10 to the negative 8 ohm meters times 0.01 meters divided by 3.0 times 10 to the negative 7 meters squared. This is equal to 0.03 ohms. For most materials, the resistivity changes with temperature according to rho equals rho 0 times 1 plus alpha times T minus T0. Where rho is the resistivity at temperature T, rho 0 is the resistivity at temperature T0, and alpha is called the temperature coefficient of resistivity. For metals, alpha is positive, and the resistivity increases linearly with increasing temperature. Such metals include iron, copper, and aluminum. For semiconductors, alpha is negative, and the resistivity decreases linearly with increasing temperature. Examples of semiconductors that behave in this manner are carbon, silicon, and germanium. There is an important class of materials whose resistivity suddenly goes to 0 below a certain temperature. Below this temperature, such materials are called superconductors. The name derives from the fact that, with zero resistivity, these materials offer no resistance to electrical current and are therefore perfect conductors. Once a current is established in a superconducting ring, for instance, the current continues indefinitely without the need for an EMF. Currents have persisted in superconductors for many years without measurable current reduction. In contrast, the current in a non-superconducting material drops to 0 almost immediately after the EMF is removed. Superconductors have many technological applications, including magnetic resonance imaging, magnetic levitation of trains, cheaper transmission of electrical power, powerful yet small electric motors, and faster computer chips. It is an ongoing field of research, and we have yet to discover a superconductor that operates at room temperature. In summary, the resistance R is a value assigned to an object that is a measure of how strongly it impedes the flow of current. It depends on the shape of the object and on the material of which it is made. The unit of resistance is the ohm. The resistivity, ρ, is an inherent property of a material. For example, rubber has a large resistivity compared to a metal such as copper. The unit of resistivity is the ohm meter. The relationship between the resistance R and the resistivity ρ is R equals ρl divided by A. Finally, the resistivities for most materials change with temperature according to ρ equals ρ0 times 1 plus alpha times T minus T0, where ρ is the resistivity at temperature T, ρ0 is the resistivity at temperature T0, and alpha is called the temperature coefficient of resistivity. For metals, alpha is positive, and the resistivity increases linearly with increasing temperature. For semiconductors, alpha is negative, and the resistivity decreases linearly with increasing temperature.